going to see the traversal technique. The traversal technique, we have the graph. This traversal technique we are going to perform on the graph. Okay, and what is graph? Graph is a cycle. Okay, and graph has a vertices and edges. Okay, and DFS, this is the short form, DFS, depth first search. Whatever in the graph, which one is in the depth, the lowest, not we cannot say the lowest, but in the depth of the graph, it will go and get the value first. Okay, one more topic is there, that is BFS. DFS, that is breadth first search. But as per your syllabus, only you have a DFS, so we are going to see only DFS. Okay, first we will see what is graph, then we will go with the DFS. So here, this is traversal technique in the unit 3, graph traversal. What is the graph? Graph is a pictorial representation of a set of objects where some pairs of objects are connected by link. Okay, connected by link. See, this is, it is connected from A to B, it is connected from B to D, connected from D to C or C to D. You can say this is called undirected graph. Undirected graph means there is no we can say this is a two-way. You can go from A to B, okay, or you can go from B to A. That is undirected graph without any arrow. Whenever we have an arrow, there is a directed graph. The interconnected objects are represented by point term as vertices. This A, B, C, D, E is all called vertices, or you can say, okay, the both has the same, but in the graph you need to say vertices, and the link that connected the vertices are called edges. These two things are very important in the graph. First one is vertices, A, B, C, D, E. Edges means which is connected from A to B, whatever the link is there, that called edges. We call edge. And what is this A, B? This is called vertice. Okay. Yes. So how will you make a formula? I hope you understand this because you have already completed the graph topic in second year. Okay. So in the data structure. So here just to show you the traversal. Okay. Formally, a graph is a pair of set, vertices and edge. Means whenever we have a graph, these two things will be there, vertices and edges, where V is a set of vertices and E is a set of edges. Connected the pairs of vertices, take a look at the following graph. Okay. So in the graph you can see A, B, C, D, E, the vertices, and from A to B and A to C and C and D to E. These are the edges. Okay. I hope you understand this graph topic. Okay, and how we can represent that as per the formula like this. How we need to write? P is equals to, how many vertices are there? A, C, E. 5 vertices. 1, 2, 3, 4, 5. Okay, 5 vertices we have. And how many edges? Edges is also 1, 2, 3, 4, 5. But we need to give the name from A to B. from A to C, from B to D, from C to D, from D to E. Okay, is the, so when we write here vertices and edges, then your graph traversal is this. Okay, now here computer science or information technology, graph traversal, also known as graph search, refer to the process of visiting, checking and updating each vertices in a graph. Such traversal are classified by the order in which the vertices are visited. So this depth first search is what it will do. It is visiting the edges, visiting the vertices. When it is visited from A to B, okay, then it is visited. So how the process is going on, how it is checking and updating or updating the vertices in a graph. Such kind of techniques are there in the graph is two: depth first search and breadth first search. But as per the syllabus, you don't have this, so just we will go with this. Okay, and depth first search will use the stack. The stack. What is the stack? What method it will follow is stack? Stack will follow last in, first out. LIFO, LIFO. Okay, last in, first out. Means whatever the vertices is going to insert the last, that will be take out first. Okay, that is called stack. Stack follow that. Okay, take the example like if we have a bunch of books. Okay, books one by one. Okay. So if you want to take a book, you cannot take this last book. Cannot take this last book. First, you need to remove these things. Okay, then only you can take this. So, what does it mean? Whatever the item is going to insert, whatever the book you are going to keep on the top, the last one, that we will remove first. So, last in, first out. So, that is what we say. Whenever you are adding here, that is called push. And whenever you are taking out from the stack, that is pop. Okay. This terminology is whenever you are inserting the item, whatever you are doing, any operation in the stack, that is pushing the data. Then whenever you are taking out from the stack, that popping. Pop. Okay. Fine. So here in the depth first search traversal algorithm, traverse a graph in a depthward motion and use a stack to remember to get the next vertex to start a search when a dead end occur in any iteration. Okay, so here it is starting from here, the first one. Okay, that it is storing in the stack example. Okay, storing in the stack, and here A, from A to D is going. Again, D is adding here. From D to G is adding. And here from G to E, and it can be go to G to F. So I am doing G to E first. Then from E to B, E to B. Okay. Is there any connection between this B? B is connected to S, but already we have S here. Sorry, okay. We have S here, so we need to pop this. Okay, after popping this, again it comes back to position E. Is there any connection here? Already G, already it is added. This also need to pop. Then after from G to F, there is a connection. Okay, there is a connection. Come back from here to here, then here to here. Again now from G to F. Now the graph will be like S, A, and F. Then from F is connected to C. This is, I am showing the roughly. I have example in the down, the bottom, that we will take the example. This all process we will do in the step-by-step process to score good marks. Okay. So here, after adding all the things, when we reach to the dead, so now we need to remove all the items from the stack. Okay. This is a process we need to perform in the depth first search. First it will go to the depth. Okay. When it is starting from S, where it is stopping here, means here dead. So this one is a depth one of the graph. Then again, okay, like this we need to perform the operation. So let's take the example and we'll solve. Before going to solve that, there is some rules. Okay. Rule number 1, visit the adjacent unvertices vertex. Means whatever the adjacent vertices, you need to visit that, unvisited. Mark it as visited. Display it, push in the stack. What we have done here, whenever we reach from S to A, this is a adjacent vertex. Okay, you can go from anywhere, here, anywhere, but I am going from here. So S to A, when I am going, so here it is showing this one is a unvisited. This was not visited in the first time, so that item we need to add in the stack. Okay, the first rule is whatever the adjacent is unvisited, that should be visited and display in the stack. Next, rule number 2, if no adjacent vertices is found, okay, then pop up a vertex from the stack. It will pop up all the vertices from the stack which do not have adjacent vertices. Means whenever, like here, just now we reach here on the B, then from here there is no adjacent vertices which is unvisited. S is visited, so here it does not have any unvisited. At that time what we need to do, we need to do the pop operation. The pop operation is remove from the stack. If it is happen to all the vertices which is no adjacent, then we need to move from the stack. Okay, then rule 3, repeat rule 1 and rule 2 until the stack is empty. Okay, until the stack is empty, we use to perform the operation. Let's solve the problem. Step 1. What is step 1? I am taking this graph. This graph S, A, C, the vertices. This vertex S, A, B, and this is my stack. What is this? First, initialize the stack. And before going to start this, you must know why we are doing. Because in this graph, we need to find the cycle, okay, and we need to know all vertices, whatever is present in the graph, that is visited or not. That is the main advantage. Means will going to know all the vertices are visited or not. Okay, so let's do first we initialize the stack. The second one, I am here now, so I mark the S is visited and put into onto the stack. Now explore the adjacent vertex which are unvisited. Okay, so we have 3 nodes or 3 vertices, 1, 3. From S going to 3 vertices. We can pick any of them. One can select anyone. From this example, we shall take the node in an alphabetic order. Okay, you can take A, B, C, anything, but we will go with the alphabetic order. So what we need to take the next? We need to take the next is alphabetic order is first A. So I am going to the A now. A is a that from the A, how many adjacent vertices which are not visited? Only one. Only one unvisited adjacent is D. Already S and D we have. So S is already visited. This is unvisited. So this unvisited, you need to select unvisited node and you need to push in the stack. Okay, you need to push the stack. From the D, we have the 3 A and C, but A is already visited and B and C is unvisited. So how we can you can select any one of this. You can select C or you can select B, but we will go as per the alphabetic order. From B and C, first will come the B. So we will select B. We will select B and add in the stack. Okay. When we add in the stack, now we have to check the unvisited vertices, adjacent vertices of B. Just check it out. S already visited, D already visited. Now, when the both are visited and it does not have any unvisited adjacent node, so you need to pop the B from the stack. Pop this B from the stack. That means no unvisited adjacent to B. Okay. So when we remove the B, so what are the remaining? S, A and D. Okay. So where is our top is D. There we are now. We are at the place of D. Now from the D, how many adjacent vertices are there? 3. A and C. But from this, which one is a unvisited? C is a unvisited. So select the C and push in the stack. Okay. C, select the C and push in the stack. Now only unvisited adjacent node is from D is C. Okay, from D and C, D to C is unvisited. So we visited and push in the stack. Okay. Now we completed the stack. Now what we need to do? There anything from the C is unvisited vertices are there? From S and D? No. So what we need to do? We need to take out the C as a pop. Then after that we have a S, A, D. From this 3, our node is here. From D, is there any unvisited adjacent? No. So what we need to do? Pop. Okay. The next is we have S and A. From A, is there any unvisited? No, all are visited. So now is pop again. Then in the last we have only S. From the S, is there any unvisited adjacent node to S? No. So just take out the S, pop, and make it empty the stack empty. Okay, stack is empty. That means in this graph all are visited. Okay, so a C does not have any unvisited adjacent, so we need to keep popping the stack until we find a node that has unvisited adjacent node. Till that we need to remove the unvisited adjacent node. In this case, there now we are keeping popping until the stack is empty. So we did the stack is empty. That means the graph has a cycle and is a connected graph. Okay, connected graph. What we say? Connected graph. Okay. So this is about the DFS, the algorithm. What is the algorithm? Whatever we are doing in the top, the example, the same thing you need to write here. First DFS, vertices, and even undirected graph. What the graph has, as I told you, two things, vertices and edges. Okay, n vertices and array visited initially set. N vertices and an array visited initially set to go. First, we are setting the 0. Okay, no one is dead. That means stack is empty. This algorithm visited all vertices stable from P. Okay, graph and visited are globally. Then we visited. Then we are popping. So visited V is equals to 1. Whenever the visited, if like S is visited, it's as a for each vertex W adjacent from P to, if anything like W means unvisited, if visited W is equals to 0, then FS W to follow all the operation. All the operation. Okay, this is about the depth first search of graph. Okay, the next class we are going to see the biconnected graph, biconnected component, and all the topics from the traversal technique. What are the articular point? Okay, so what we have done today? So traversal technique, we saw the graph and we completed the depth first search example as well as the algorithm. Okay, thank you very much. We'll see you in the next class. Connected components, and we are going to see the biconnected graph, biconnected component, and last one is articular point. What is this? All these things we are going to cover in today's lecture. Okay, and this all will come under in traversal technique. Okay, so now first one is connected graph. What is connected graph? A graph is connected when there is a path between every pair of vertices. Okay, like this is a graph, and what is the vertices? This is a vertices. These points, can you see this? These all are the vertices. Vertices, and whatever this line is connecting the links, this all called edges. Okay, so what is the connected graph? A graph is connected when there is path between every pair of vertices. So it's connected all graph, like here edges, here edges, and it's all connected together. Okay. In a connected graph, there are no unreachable vertices. A graph that is not connected is disconnected. When we say the disconnected, like you can see this dotted line here. Okay, this dotted line, if we remove this, then it will become a two graphs. So when the two graph is there, so it is not a connected graph. Now this graph and this graph, these two graphs is connected with this line. Okay, so now this is a connected graph. No one edge is left here. This graph becomes disconnected when the dashed edge is removed. When you remove this line, then it will become a disconnected until it is a connected graph. A graph G is said to be disconnected if there exist two nodes in G such that no path in G has those nodes as endpoint. This vertices also known as nodes. Okay. Like if we have our point A and here is B, okay, but these two are not connected together. So this is called disconnected. What is this? Disconnected. This is a, okay. A graph with just one vertex is connected, and edgeless graph with two or more vertices is disconnected. So at the time also it is a connected. Okay, connected is nothing but every vertex should be connected together with all vertices. No vertices should be left out. If you see in the graph 2 here, with vertex 0, this graph is disconnected. The rest of the graph is connected. So this 0, the disconnected, all 1, 2, 3, 3, 3, 2, these all are connected. Okay. When all the vertices is connected with link, there is nothing but edge, then it will become a connected graph. I hope you understand about the connected graph. Now we will see the connected components. What is connected component? In graph theory, a connected component or just component of an undirected graph. Undirected graph means, like example, A, B, C, D. These four vertices are there, and I am connecting this. So I am giving the arrows. Okay. I am giving the arrows. So here, whenever the graph has the arrows, then this is a directed graph. Directed graph means from A to B, it will go from A to B, but it cannot come back from B to A because the arrow mark is here. This is a directed graph. What is undirected graph? Undirected graph example is this. Here we don't have any arrows, so it will go from here to here, from left to right or right to left. Means from A to B or B to A. So when the undirected graph is there, in that the direction is not mentioned, so you can go from A to B or B to A. So here undirected graph is a subgraph in which any two vertices are connected to each other by path, that is edges. Okay, there will be a path going from A to B or B to A, and which is connected to a non-additional vertex, that is a supergraph. Okay. So here in the graph, if you see, it is a set of vertices in a graph that are linked to each other by path. Can you see this one? This all edges are known as path also. The nodes pair are connected only if they belongs to same component. So how many components are here in this graph? Here 3 components are there. A graph with 3 connected components. Okay, one is this. Okay, and one, 2, and this middle one is 3. So 3 connected components are there. No edge is left out here. That's why we are telling that this is a connected. Okay. So this is undirected graph and directed graph. You must know about this. Okay. Next point is strongly connected components. Strongly connected component. What does it mean by strongly connected component and connected component? A graph is said to be a strongly connected or disconnected if every vertex is reachable from every other vertices. So here, when it will be happen, if you have an undirected graph, then you can say it is a strongly connected. Why? Means you can go from one vertex to all the vertices. If you have a graph like this, then your graph is a strongly connected. Okay. Here, from 1 I am going to 0, from 0 I am going to 3 and 4. So from every other vertex, okay, you can be reached to all other vertices. Then only it will be a strongly connected component. In this given graph, you can see the strongly connected component or disconnect component of the arbitrary directed graph from a partition, okay, into subgraph that are themselves strongly connected. Example, if we remove the edge between 0 to 3, if we remove this, okay, then only after that also it will be a strongly connected graph, because it all are connected together. Strongly connected component, SC, strongly connected component. Strongly connected component of a directed graph is a maximal strongly connected subgraph. If, for example, there are 3 strongly connected components, the following graphs: 3, 1, 0, 2, and 3, 4 is another graph. This is a strongly connected component. What does it? When it will be a strongly connected component? When every vertex is reachable from every other vertex, then only it will be a strongly connected. If I take the example of 1, if I go from 1 to 0, 0 to 2, yes, I can reach all the vertices which are present in the graph. If I take the example starting point as a 0, then from 0 I can go to 2 and 1. Yes, possible. If I take the example of, if I take the vertex 2, if we check here from 2 to 1, 1 to 0, yes, so that means it is strongly connected. You can select any vertex, from there you can reach all the vertex which are available in the graph. Okay, so here the next is connectivities. Connectivity in an undirected graph means that every vertex can reach every other vertex via any path. So what is a strongly connected component? Strongly connected component is like you must go from any vertex to all the vertex which are present in the graph. Okay, but here in the connectivity means you can go with any path, but you must complete all the vertices, then only it will be a connectivity. Okay, from A to H if we take the example of A to H, is going through so many vertices, but it should be reached to H, then only it will be a connectivity. If the graph is not connected, the graph can be broken down into connected component. Okay, example, if we don't have a graph to reach, like if you want to make a connectivity, a strongly connectivity, then you need to make a component. When you make a component, you can divide the graph in subgraph. Strongly connected apply only to directed graph. A directed graph is strongly connected if there is a directed path from any vertex to every other vertex. This is an example. You can see here the dotted line 1, 2, 3. Okay, 1, 2, 3. So it is divided into 3 subgraph, and why means we need to change the graph into a strongly connected graph. Okay, and this is a directed graph. Why it is directed graph? Because here it is mentioning the arrow. Okay, it is mentioning the arrow, so it is a directed graph. Similarly, to connected component, a directed graph can be broken down into a strongly connected component. When we break down this, then it is a strongly connected component. You can take the example of A. You can go from A to B, B to C. Okay, we remove this F and G. 3 subgraph, and this all 3 are the strongly connected component. Okay, one more time I am telling what is strongly connected component. Strongly connected component, from every vertex you should reach all the vertex in the graph. So here A, you cannot reach, you cannot make this all complete graph as a strongly connected. So we break down into a connected component, then it will become a strongly connected component. Okay, so this is a 3 subgraph. Okay, procedure to finding connected component. Okay, now the biconnected graph. In the biconnected graph, so how many topics we completed till now? We completed the connected graph and connected component. Okay, now we are going with biconnected graph. In graph theory, a biconnected graph is a connected and non-separable graph, meaning that if any vertex were to be removed, the graph will remain connected. Therefore, is a biconnected, has no articular point. So here, if you remove any edge, like in the previous example in the connected graph, if we remove any edge, okay, between these two example, if we remove this, then it will become a 2 subgraph. Okay, so this is not a biconnected graph. If we remove any one of the edge, so that should not divide into 2 or 3 graph. Okay, 3 or 2 subgraph. That should not be a 2 or 3 subgraph, and there should not be a articular point. What is articular point? An articular point is a connected graph, is a vertex that if delete would break the graph into 2 or more pieces. Connected component, biconnected graph, a graph with no articular point called a biconnected graph. So what is articular point? So here some of the examples. Here, like this is a biconnected. Why it is biconnected? Because if you remove this example, it is dividing into any other subgroup? No, still it is a one group. Example, if this is okay, now if I remove this example, still 1 0 2 4 3, still it is a one graph. Okay, no problem. You can remove any edge. If I remove this 1 0 2 4 0 3, yes, still it is a connected graph. But here, if you come to here it is a articular point. If I remove this, what happened? It is one group and it is a second graph. This is first graph, second graph. It is divided into two subgraphs. Because of that, it is not a biconnected graph. Let's check it out. This not a biconnected. Let's check it out. Why it is not a? Here, if I remove this example, 1 2 0 3 4, yes, okay, no problem. But if you come to here, this, okay, if I remove this edge, then what will happen? This will become a 1 and this will become a second, 1 and 2. So here it is dividing into two subgroups. So that means it is not a biconnected graph. Okay. And here, if I remove this example, this is also not a biconnected graph. So I hope you understand biconnected. Here, it is a biconnected graph. How? If I remove this, it is not dividing any subgroup. 1 2 0. Okay. If I remove this also, if I remove that, then only the graph is connected into a single graph. So it does not have any articular point. Articular point means if you remove any one of the edge, then it will become a separate group or more than two groups. Okay. So this is how to find the given graph is a connected or not. With the help of articular point, we can identify the graph is biconnected graph or not. A graph is biconnected if it is connected and does not have any articular point. We mainly need to check two things in a graph. The graph is connected. First, there is not articular point in the graph. These two things you need to check the graph to check the biconnected graph in the same way what I shown you in the 4 example. Biconnected graph, not a biconnected graph, and this is also not a biconnected graph. A biconnected graph. Okay, so now let's check it out. What is biconnected component? In graph theory, a biconnected component, also known as a block or two connected component, is the maximum biconnected subgraph. Any connected graph decompose into a tree of biconnected component called a block cut tree. Okay, block cut tree. Let's go and check the graph. Okay, so here in this graph, okay, biconnected component. So this graph, how many ways we can break out? Okay, this is a graph. Okay, and this graph is break out in this many components. So this all are the biconnected components. Okay, so here you can check it out. 1 2 3 4, this is 1, and here 0 1 2 8 7 3 9 7 4, and here 3 5 5, and here 5, 7, 6. So this is a biconnected component. So whatever the biconnected graph is there, we need to change into a biconnected component. How will you do? With the block code tree. Okay, any connected graph decompose into a tree of biconnected component called the block cut tree of the graph. Okay, this is the connected graph. This is a connected graph because it has a articular point here. Articular point. So this is a articular point, then it is a connected graph. It is not a biconnected graph. So we block out the graph, connected graph, into a biconnected components. Okay. So here in the graph G, that is not biconnected. Okay, this is not a biconnected. How? Because it has so many articular points. Okay, like example, if we remove the edge from G to H, then it will become a two graphs. Or if we remove this G to J, then it is divided into subgroup. So this is not a connected graph, biconnected graph. Okay, let's remove this. Okay, so the graph G, that is not biconnected. Yes, this graph is not a biconnected. And what are the articular point here? Articular point here is A. If I remove this A, okay, if I remove A, so 1, 2, this all is divided. Okay, so A, H, B, J, A, H, J. These all are the articular point. Okay, and what are the biconnected components? Like seam above like this. Biconnected component A, C is connected here, D is connected here, D is connected here, E is connected here, and F is also connected. B is not a biconnected component here, but the graph. Okay, this is a separate. Next, from G, J to L and P. This is how we are getting if we go from A to G, G to J, J to L, A to B. Okay, these are the biconnected component E, H, I, K. Fine. So here, now the last topic of today's lecture is articular point. What is articular point? If any edge, if you remove from the graph, then it will divide into two or more subgraphs. That is called articular point. So the blocks are attached to each other at shared vertices called cut vertex or cut point or articular point. This is the three name of the articular point. First one is cut vertices, and cut point and articular point. Especially a cut vertex is any vertex whose removal increase the number of connected components. Okay, if we remove the edge, okay, or if we remove the vertex, then it will be increase the number of connected components. A vertex in an undirected graph in an articular point, if and only if removing it and edge through it disconnected the graph. Articular point represent vulnerability in a connected network. Okay? Whatever we have discussed in the connected graph, in the biconnected graph, like in the connected graph, if we remove any one of the edges, then it will make a 2 or 3 graphs. So that is called a articular point. Okay, so the articular point examples are here. Following are some example graph with articular point. So here, what is the articular point? Here is 0 and 3. If we remove any one of this edge, or if we remove the vertex, then it will divide it into more than one graph. Okay, will divide it into subgraph. So here articular point, what are the articular point here is 2 and 1. 0, 1, 2, 3, this is a graph, and here 1 and 2 is a articular point. If we remove this, you cannot reach to 3. So okay, next articular point is 1. So here this graph, if we remove the 1, if we remove this, then 0, 2 is a one subgraph, 6 is another subgraph, and 3, 5, 4 is another subgraph. So it is divided into 3 subgraphs. So this is a connected graph, but this one is a articular point, and this is, if you remove this, then your graph will divide it into more than one graph. So time complexity is same as a DFS, which is order of vertex plus edge for adjacent list represent of the graph. Adjacent list representation of graph. So what is the time complexity of depth first search? Order of B plus E, that is vertex plus edge. Now the question is how to find all articular point in a given graph. A simple approach is to one by one remove all vertex and see if removal of vertex causes disconnected graph. Following are steps of simple approach for connected graph. For every vertex V, do follow. Remove V from the graph. First you need to remove the vertex. See if the graph remain connected. We can either use BFS or DFS. You can try any depth first search or breadth first search. Check the graph is connected or not, and be back to the graph. After that, if it is still connected, then add the same vertex, whatever the vertex you remove, just add that back to the graph and remove the another vertex. So do this, follow these steps again and again until you will find you reach all the vertices. Then only you can say it is a connected graph or a biconnected graph. Or you will going to identify is there any articular point is there or not. So this is about the today's lecture. So what we have completed today: connected graph, connected graph, connected component, biconnected graph, and biconnected component, and articular point. Okay. Articular point is another name is cut point and cut vertex. Okay. So the articular point very important. So here the simple I will say here, in the connected graph, if we have an articular point, no problem, because that will say the connected graph. Okay, but if you have an articular point in the biconnected graph, then that is not a biconnected graph. So in simple word, if you have an articular point in the connected graph, no problem, but if you have a biconnected graph, if you have a articular point, then you cannot say that is a biconnected graph. So this is about the today's lecture. Today we completed this. Okay, connected graph, connected component, biconnected component, and articular point. Thank you very much. We'll see you in the next class.